Hi everyone! In this video we are going to go over the E2 reaction mechanism in a little more detail. So previously we said that an E2 reaction is a concerted second order reaction. And concerted means that everything happens at once. So a base will come in and grab a proton, which will leave behind electrons to create a double bond, and then the leaving group leaves. So that all happens in one step. So that is a concerted reaction. And then we also said that beta protons are deprotonated by a base. And one last thing that we are going to cover here is that beta protons in a cyclohexane ring need to be anti-coplanar with the leaving group. Now, remember that anti-coplanar means that the proton is opposite from the leaving group, or opposite in the same plane. So let's kind of go over that. Let's look at an example because this might not make sense right away, and that's okay. All right, so let's say we have a cyclohexane ring and we have a bromine in a wedge position at the top. And let's say this is reacting with potassium tert butoxide. So this is a bulky base, which means that it will not act as a nucleophile, which is perfect. So the base, remember, is going to take a proton from a neighboring carbon, so a beta carbon. So let's label our alpha carbon. So remember, that's the carbon bonded to the leaving group. And then we have the beta carbon next to that. And there's actually two beta carbons here, but we'll just focus on the one to the right just because it's easier. All right, so that beta carbon has two hydrogens bonded to it. And tert butoxide could take one of those protons, but it actually wants to take the proton that is anti-coplanar with the leaving group. So let's label our protons A and B. And let's redraw this molecule in a in a chair conformation, because that will help us to figure out which hydrogen is anti-coplanar to the leaving group. Okay, so let's label arbitrarily this upper right carbon as the alpha carbon. And then we'll label the bottom right carbon the beta carbon. And then we have another beta carbon up above as well. But we'll focus on the alpha carbon and the beta carbon to the lower right. So looking at our original molecule, bromine is pointing up. And looking at our chair conformation, the alpha carbon is pointing up, which means we have an up axial position and then a down equatorial position. So bromine has to be up, so in this case it will be axial. And then there's a hydrogen on the other bond. Now looking at the beta carbon down below, that's pointing down, so we have a down axial position and an up equatorial position. So looking at our original molecule, HA is up, so that will be equatorial, and HB is down, so that will be axial. So anticoplanar means that the hydrogen will be opposite the leaving group in the same plane. So let's just write that down. Opposite the leaving group in the same plane. So that would be HB. HB is opposite bromine in the same plane. HA, however, is off on its own adventure over there. So it is not opposite bromine, and it's equatorial. So to be anticoplanar, the leaving group and the hydrogen have to be axial. So axial positions are required. So if we look at the word anticoplanar, coplanar tells us that the groups are in the same plane. So bromine and HB are in the same plane. And then anti means that they're opposite each other, which we can see bromine is up, HB is down. All right, so all of this tells us that tert butoxide is going to preferentially take HB. And then the shared electrons will be left behind in a double bond or a pi bond. And then bromine is going to leave. So our products we would have a double bond between the alpha and beta carbon on the cyclohexane ring. Tert butoxide will take a hydrogen, so we'll end up with HOTBU. And then we also have our leaving group, the bromide ion. And that might be balanced by the potassium that we had before. So you could write KBr potentially there. All right, so again, if you're trying to figure out, let's say, which hydrogen is going to deprotonate, it has to be anticoplanar to the leaving group. Okay, so let's look at another problem. Let's get a little more practice here. Let's say we have just a generic leaving group. And I'm just going to put an R group, an alkyl group, off to the left. So you can kind of ignore that side of the molecule for now. And let's say that this reacts with just a generic base. Okay, now we have to figure out what is our product and which hydrogen will be deprotonated. So first things first, let's find our alpha carbon. So again, the alpha carbon is the carbon bonded to the leaving group. And then our beta carbon is right next door. So we know that the base is going to take a proton from the beta carbon. So let's draw all of the hydrogens on that methyl or primary carbon there. So we have one up above that's planar, we'll have one in a wedge position, and one in a dash position. And I'm going to draw these in different colors so we can keep track. So the top hydrogen will be blue, the wedge hydrogen will be green, and then let's draw the dashed hydrogen in orange. All right, so which one of those hydrogens will the base want to remove? And remember, it has to be anti-coplanar. Now, we don't have a ring system here, so we can't draw a chair conformation to figure this out. Instead, we're going to draw a Newman projection to figure out which hydrogen is anti-coplanar. So let's look down this bond here. I didn't draw that very straight, but you get the idea. So we're going to put the beta carbon in front of our Newman projection and then the alpha carbon in the back. So let's draw the beta carbon in the front, and remember there's 3 hydrogens on that beta carbon. So the blue hydrogen is up above. The dashed hydrogen, if we kind of turn that molecule towards us, the dashed hydrogen is to the right, and the wedge hydrogen is to the left. All right, now let's draw the alpha carbon in the back. So if we're turning the molecule towards us, so kind of turning it to the left, the leaving group is in a wedge position. And so that will face, let's see, the left. There is a hydrogen in the back, so that will be to the right. And then the R group is on the bottom. Okay, so looking at our Newman projection, we can see that the orange hydrogen is opposite the leaving group. So they're in the same plane, but opposite each other. Okay, so that means the base is going to take the orange hydrogen, and then we'll leave electrons behind to create a double bond, and then the leaving group will leave. So initially, we have this alkene that's shown in the products. And let's also show all of the hydrogens, just to see where they end up. So on the alpha carbon, which is the one to the left, we have just a regular hydrogen there. And then to the right, on the beta carbon, we still have a blue hydrogen and a green hydrogen. And the blue hydrogen, it looks like, will still be up above. And the green hydrogen will be down below. So looking at our Newman projection, we can also figure out which groups will be above the plane of the alkene and which will be below. So we can see that the blue hydrogen will be on the same side of the molecule as the black hydrogen. So those are cis to each other. And looking at our product up above, the black hydrogen on the left and the blue hydrogen on the right are on the same side of the double bond, so that makes sense. And then looking at our Newman projection again, the green hydrogen and the R group will be cis to each other. And looking up above at our alkene, that is true. The R group and the green hydrogen are on the same side of the double bond. Okay, so you can imagine that this can get a little trickier if we start adding other types of groups onto our molecule. So, maybe we have an isopropyl group somewhere or an ethyl group somewhere. How do you figure out what's on the same side of the double bond? And drawing a Newman projection can help to figure that out. All right, so I think we'll stop here for this video. I just wanted to show you in a little more detail how an E2 reaction occurs. So again, the base is going to take a hydrogen that is anti-coplanar to the leaving group. And we saw how to figure out which proton is anti-coplanar for a ring system. So we draw the chair conformation and we make sure the leaving group is axial. And then whichever hydrogen is opposite that axial leaving group is the anti-coplanar hydrogen. And then for just a regular molecule, a straight chain alkane, we would want to draw a Newman projection, and whichever hydrogen is opposite the leaving group is the anti-coplanar hydrogen, and that's the one that the base is going to deprotonate. And then we also saw how to figure out what's above the double bond and what's below the double bond. Okay, so in the next video, we're going to go over some other practice problems, and we're also going to learn a few new definitions, so how to define a reaction based on the types of products it forms. So I will see you there.